Hello.
Yes.
Yeah, I'll begin.
Yes, please.
Yeah, so we had looked at a technique to merge neurons at the cost of approximating the behavior, or in this case, at the cost of computing a bigger output at the output neuron that we have for every input. So we know of one way of merging neurons such that the resultant network computes a bigger output for every input value. And this, we also saw that this could be fine as long as you're checking a property which is which in some sense is, it allows you to do this kind of an abstraction. But if you're checking a property which does not allow you to do a lot of merges, then you need to worry about how much to merge or which ones to unmerge, right? So this is something that we saw in the last class, that if in some sense if you have abstracted too much, and that you will know only when you are checking for the property, and if you get an example which turns out to be spurious. So whenever you get a counterexample, you can actually simulate it on the network, and then you can quickly check if that is spurious or not. So checking a counterexample whether it is spurious or not is not very expensive. You can run a simulation and you can check it, right? So
yeah. So here I want to ask Amaya, so is it clear to you as to why, if the verification fails on an after you abstract, that it may be a real counterexample or not real, or maybe an error? Or
yeah, sir, it's clear why.
Why? Can you explain?
Like it's basically so it covers all the. It's an over approximation, right? So in an over approximation, it doesn't, like, if it's only if it satisfies the property can you say that the underlying thing is also true, or else it's incorrect.
Be more specific, okay? Suppose your property is some y that you're trying to verify is y is greater than c.
Yeah, so if your abstraction is greater than c, then you know that your original is also greater than c. But if it's not, then you don't know anything about it.
Yes. Okay. So it could be, or it could be true, or it may not be true, because for that particular input, the counterexample is saying your property is violated. Your over approximation may be returning the correct one, or maybe returning greater. You don't know. Huh? So that's why. Yeah. Okay. Good. So
yeah.
Make sure that you understand it, and that is one way of doing it. Checking if it is real counterexample is actually simulating. Yeah. Okay.
Correct.
So
yeah. So when you obtain a counterexample, you can check whether it is spurious or not. If it's real, then you're done, because you have a counterexample to your property, and this checking you do on the original network, of course. But if it turns out to be spurious, then you need to find out how to create a better abstraction, in the sense that, how do you put some information back into the system. And the way to put information back into the system is by doing a refinement, where you take a merged node, and then you remove a neuron from the merged node and restore it in the network. So this is what you do. So in that sense, so one of the things which is important to understand here is that, suppose you take a big enough merged thing which has 5 neurons. So you cannot split it in 3 2. You cannot do this kind of a refinement. The only refinement that these guys propose or allow is that, you can pick any one of these and restore this back into the network and have a merged one of the other 4. And why do they do that? So the reason they allow only this kind of a refinement is because, when you compute a 3 2 split, then you will have to, you don't know what are the values of these, what should be the weights on the incoming edges to this and from all the neurons, and what should be the weight of the incoming edges to this from all the neurons. The outgoing is still very simple because you can take these three and sum the outgoing. Okay, but this is not what they allow. They only, I believe that this is the only splitting heuristic that they've suggested, is that you take a neuron which is, take any of the component neurons which is there in the merge or in the abstraction, in any one of the abstractions, and remove it and restore it in the network. So you will know all the weights on both sides of it from the original network itself. And but I've not thought about this very much, but I think it's also possible to do a 3-2 split. So if you have a 5 neuron abstraction, then it's also possible to do this kind of a split. This will also restore some information back into the system. For instance, if you think about it, what is happening? So when this got abstracted, suppose this got abstracted, actually, there was a neuron of 3 and there was another one of 2. And this got abstracted because, there were these 3 came in here because you took the maximum of the incoming edges of these 2, and then the maximum of the incoming with that one. Suppose this is an increment neuron. So you took the maximum one of these 2 and then the maximum one. So somehow you ended up taking the maximum of these 3 and then the maximum of these 2. And now you're taking the maximum of all the 5. And somehow, this is the weight that you assign. Now this maximum of all the 5 could be a much bigger number as compared to, keeping 2 copies with 3 and this 2. And if you restore, so basically the point that I'm trying to make is that even if you refine it in this form, you are making it more precise, certainly. So this is making it more precise. Okay. And this can be done. But remember that, in order to do anything of this sort, you need to have the original network in mind. And when you restore these edges which you had omitted, then you will have to find out the value of these edges from the original network and recompute. So there's some amount of bookkeeping that's needed in order to get your refined network. Okay, so that's what
you do one at a time. It's also possible to do what you're doing by doing one at a time.
It's also possible to do.
But the reason that I'm wondering why you're suggesting this way to do, will it be any better, or will it be more efficient to do this? I mean, unless you can make obviously in the last class you introduced a measure.
Correct, which I'll come to.
So then they'll have to come up with a kind of a measure for these kinds of splits as well. So
correct. So
the analysis that you will have to do.
Correct. So the downside of this is, see. So when you have a merge thing like this, so suppose you have a merge thing like this. There's a figure right here. So if you have a merged neuron of this kind, then there are only 3 possible ways of refining this. You either remove this one, or remove this one, or remove this one, right? But if you are now exploring all possible ways of splitting this into 2 sets, then you'll have to worry about more possibilities in general, right? So that is one problem. It leaves you to worry about.
The analysis is more expensive, no?
The analysis is more expensive, and secondly, it's not clear how do you prioritize a particular subset over some others. Okay. So they are trying to, so in this paper,
but that's where I said that if you're able to extend this measure to any splits, I mean, whatever, they're presumably using some measure or to say, oh, this split is better than the other split. Okay. So in that sense, maybe you can, you can use the same measure if it is applicable to any kind of splits. That I don't know. I mean, right now, the way that you have defined these measures is for splitting one, taking one at a time. So
Correct,
what I'm
correct.
saying is you will have to then extend that measure to, any arbitrary
To taking a subset at a time. So
space
there
as
are
well.
two,
In
yeah, so there are,
addition to,
correct. Yeah. So there are two problems with this. One is that, how do we extend this notion of how much is being restored? So extend the measure to work on a subset instead of a single neuron. And secondly, even if we are able to do this, for instance, let's say that, there is some measure that we are able to calculate for V1, and there's some measure that we are able to calculate for V2. Now for a subset, let's just add the individual numbers, whatever is the measure that we are getting. So even if we extend it in a very simple way like this, I'm claiming that, the reason why they are not worrying about subsets is because even if you are able to extend this notion, to worry about all 2 to the power n subsets is a lot of work. And so there are two problems with this. One is, how do you extend the measure in the best possible way? Maybe, you can certainly maybe add the measure of, how much is being restored. One such measure we had seen in the last class, which I'll go over again. So you can add these measures, but even if you add these measures, you'll have to worry about 2 to the power n subsets, and which is why I believe that they don't do it. But yeah, but once again, these I have not thought about these very much. So these are in some sense, open to discussion. Okay. So we had looked at merging heuristic, and we decided that, in merging heuristic, we had seen that it would be nice to merge neurons such that, so for instance, in this case, I think, V1 and V3 was being suggested for merging. And the reason why this was being suggested for merging is because, if you look at the pairwise difference in weights, if you looked at the pairwise difference in weights, then you found that, this was the one with the least amount of difference, which means that what are you going to be doing? So this is the X1 has an edge going here with a weight of 1, and it's going here with a weight of 2. If you merge these two, both of these will get a weight of 2 each, the maximum one here. And so that the maximum remains closer to the individual weights, you want to find out the pair for which the individual weights do not differ by too much. If the individual weights do not differ by too much, the maximum will be closer to the individual weights. And that's why you will do the least amount of over approximation when you choose such a heuristic for merging. Okay, so this is something that we had seen. Okay, for splitting, we decided that we will rely on two things. So the first thing that we decided that we'll rely on was the difference that the difference between the values being computed by the abstracted neuron and by the original neurons, the individual neurons. So let's look at this difference. Okay, so consider a counterexample that you get by checking that your abstraction is insufficient to discharge the property. So you get a counterexample which turned out to be spurious, and now with this spurious counterexample, you are looking to refine the network. Okay, and suppose you decided to split one of these three. Okay, so if you have decided to split one of these three, then they say that you look at for this input, you look at the value computed by this merged neuron. So for this input, the value computed by the merged neuron, so the input is 1 and 0, so this is 1, this is 0, so the value being computed by the merged neuron is 1 times 4 plus minus 1 times 0, which is 4. Okay, which is this value here, 4. Okay, and then they say that you for the same input, you look at what these three neurons would have gotten individually. Okay, so for this input 1, 0, let's see what these three individual neurons would have gotten. So for 1, it would have gotten 1 into 1 minus 2 into 0. So this would have gotten 1. this one would have gotten 1 into 4 minus 1 into 0. So this would have gotten 4. And this one would have gotten 1 into 2 minus 3 into 0. So this would have gotten 2. So this is 1, 4, and 2 here. Okay. So they say that now look at this, the difference between these values that are being computed here. So the abstract would have computed 4. The original would have computed 1, 4, and 2. So the difference between these weights is 3, 0, and 2 for V1, V2, and V3. Okay. So this is the difference between these. Okay. So what is the idea here? So we want to restore one neuron for which this difference is the largest. Okay. So this tells us, if you only look at this part, it tells us that we should try and restore V1, because this difference, because if you abstract and merge V1 with the other things, then the value, the abstracted value of V1 deviates by the largest amount from its original value. Okay. So this was 1. If you put it in the merged thing, then it becomes 4, and therefore this deviates by the largest amount, which is 3 in this case. Okay. This one does not deviate at all. This one deviates by 2. Okay. So therefore it tells us that let's pick this. Okay. So this is one heuristic that they use. They say that you should restore the one which has deviated the most. Okay. But this is not the only thing that they use. They also use what is the weight difference between. Okay. So the weight difference between, so this is the counterexample guided part of it. So this is coming from the counterexample. Sorry. This one is the counterexample guided part of it. And this one is not coming from the counterexample. Okay. So you're simply looking at the difference between the weights. Okay. So X1 is sending 4 to the merge thing here, and X1 is sending. So let's
before you do that,
yeah.
Just to make sure, I asked a question to Ameya. So Harsh, you're here now?
Yes, sir.
Yeah, did you understand the reasoning that Madhukar explained as to why this criteria, picking that node which has the maximum of the difference, the one to split, the one to choose to restore?
I mean, you mean like the heuristics merging?
Why does that heuristic make sense? What is the rationale?
So I mean, like, wait, let me remember the heuristic. So the heuristic was that you pick the smallest difference one, right? I mean, it makes intuitive sense.
No, here he's picking the largest difference.
After for splitting one, like, I mean, it makes sense to go in the reverse order of merging. I mean,
why?
But
my simple question is why? Just to make sure that you that all of us understood. That's all.
So like I didn't get the counterexample guided part.
The counterexample is being used to do it based on the counterexample. Yeah, I mean, if you split, if you restored V1 as opposed to V2, you will restore in some sense the more. By doing that, you will get
the best possible,
more accurate. Okay, more accurate than if you say restored V2.
Yeah, more bang for buck. Like for a single operation, you will reduce it by best possible amount.
Yeah. Now, I think you didn't understand how counterexample helped there. Maybe Madhukar that you.
I mean, I actually like have some intuition why they would work, because for example, if you're only interested in a certain kind of counterexample, then I think like we could cleverly split it. So as to-
No,
Yes, I like me. Yes, maybe.
I think you should explain because so the counter example is the only guide that you have here at this point. Okay, yeah, maybe you
Yeah.
should.
Okay.
Right.
So the abstraction part we understand. Abstraction was the one where we were, when we were merging, we were looking at the one where the difference between the edge weights, we were trying to minimize the difference. Right, Harsh? You
Right.
remember? Yeah.
What could you repeat what you said?
No, I'm saying that, when we are doing this abstraction, we were trying to minimize the maximum difference between the edge weights, right? And the intuition behind minimizing the maximum difference was that, when we are merging, we end up taking, for instance, in this case, if x1 is sending a 1 here and x1 is sending a 2 here, then we would end up, if we merge v1 and v3, then we would end up replacing this 1 by 2, right? The maximum one.
Right.
And so for the maximum to be closest to all the other individuals, it's important to pick ones where, the difference is not so much. Okay. So if you pick 1 and 2, the maximum is 2 and the maximum is kind of close to both these things, right? But if you pick something which is 1 and 20, then the maximum is 20 and the maximum is very far from one of them. Correct?
Yeah, but I thought his question was, how is the counter example being used?
Yeah, no. I went a step back and told him about this abstraction. So Harsh, is this part clear?
Yes, sir.
Yeah. Okay. So now when we are splitting.
Yeah, I guess it's the reason counter example comes into picture is because after you do the abstraction, you try to verify the property, and the property fails. Giving a counter example. I think you missed the first part. Since you came late. Okay, so in the first part, then you check. Okay, when the verification fails, Madhukar explained, you don't know. It could be a real counter example or not. It could be a real error or not an error. Okay. Let's suppose it is not a real error. If it's a real error, then you're done. You have found an error. Okay. If it's not a real error, then you have the counter example. Okay. And that's when you use that to compute.
Refine your loop.
Yeah, I think that part he explained that you came in late for. Yeah.
Okay.
Yeah. Okay. So once so I think so this we understand that if we are trying to abstract the original network, then we may get counterexamples that are spurious. If we get a real counterexample, then we are done. But if we get a spurious counterexample, then this needs we need to refine the abstraction in order to get rid of this. So one measure that they suggest to find out which neuron should be split and restored into the network from a merged node is that they say that for this counterexample, so suppose you want to split one neuron from this one. Okay, so suppose that you've decided that this is the layer in which I'm going to do a splitting, and this is one merged neuron from which I'm going to be doing the splitting. How do you decide the layer? How do you decide the merged neuron? These are questions that we can discuss later. But if you take a merged neuron, how do you decide which one is the best neuron of these to be restored back into the network? Okay. So what they're suggesting is the following. So they say that you take your counter example and then you evaluate for this counter example, which is 1 and 0. So let's put 1 and 0 here. So they say that for this 1 and 0, what is the value that you will get at the merged neuron? So at the merged neuron, you will get 1 into 4 minus 1 into 0. So you'll get 4 here. Okay. And they say that let's compare this to the values that they would have gotten in the original thing where each of them were individually a neuron for the same counter example. So for the same counter example, this would have gotten 1 into 1 plus whatever into 0. So this would have gotten 1. This is 1 into 4 here plus 0 from this side. So it doesn't matter. And then 1 into 2 minus 3 into 0. So this would have gotten 2. So now they're saying that, look, V1 individually would have gotten a value of 1, at least for this counter example. V1 would have gotten an individual value of 1. V2 would have gotten an individual value of 4. And V3 would have gotten a value of 2 individually, right? And if you have merged the whole thing, then everything is getting a value of 4.
Yeah, I think that is already explained. Yeah.
Right? So what's happening is that they pick the neuron for which this deviation from the original is the maximum. Okay. So this is the deviation in this case, in case of V1 is 3, the deviation in case of V2 is 0, and in case of V3 is 2. Correct?
Correct.
So
So
they say
like,
that you pick something, you pick the first one so that, you restore. The first one was in some sense, adding a lot to the over approximation. So let's
so you
remove that.
do the same thing. So you just pick the best one, which gives bang for buck, but like fixes the counter example.
Well, whether it fixes the counter example
Correct.
is unclear. Certainly, it restores the maximum accuracy, okay, among the 3 possible choices that you have for the split.
Correct.
Oh,
Whether it restores, whether it eliminates the counter example or not is unclear.
Correct. So in fact, they claim that, by doing such a restoration, you may not immediately eliminate a spurious counterexample, but a sequence of refinements will eventually eliminate.
oh, it's a heuristic.
It's a heuristic.
That's right, because because you don't know how much because there are other neurons, presumably, correct, Madhukar? I mean,
Correct.
that would have merged. Okay, so how much do you need to restore? How many do you need to restore to eliminate this particular counterexample is unclear. But at least you're making progress towards that objective, towards that goal.
Okay.
Correct. Okay, so this because we arrived at these values by looking at the counter example. So therefore, we call this a counter example guided way of picking the neuron to refine, right? So this is a counter example guided refinement in that sense. Okay, so this is a counter example guided way of refining. But this is not the only thing that they suggest. They suggest that, in addition to this, let's also look at the weight differences. Okay, so now, and this is not the counterexample guided part. So let's see how this works. So they say that let's look at the weight difference between V1 and the merged neuron for edges coming from these two. So what is the weight difference between the edges coming from this the input, whatever, from the previous layer to the merged thing and to these individual things? So x1 is, there is an edge of weight 4 coming from x1 to this one, and from x1 to this one there is an edge of weight 1. So this is 3 is the difference. Okay, now from x2 this is -1, and from x2 this is -2. Okay, so this is -1 -2, so whatever, this is 1. This difference is the absolute value of this difference is 1. Okay, so this is 3 and 1 is the difference in the weights. The bigger one is 3 here. Okay, similarly, you look for the weight difference between V2 and V1. So from V2, so this, the first one will be the same here. This is 4, but this one will be 4 minus 4, which is 0, and this will be -1 -1, which is 0. So this is 0 and 0, and the biggest value is 0. Okay, similarly, this one is sending a 2 here, this is sending a 4 here, as we have seen. So the weight difference is 2, and from x2 also this is -1 and this is -3. So the weight difference is 2 here, so the biggest is 2. And they say that here also you pick the biggest. Okay, So this is analogous to, how you were looking at the weight difference between the edges when you were abstracting. So this is analogous to that, but this is not a counterexample guided thing. This is a counterexample guided thing. So they say that let's combine these two. So you calculate this weight and basically, this measure, and then you multiply the two. And then you restore the one which gives you the maximum benefit with respect to this multiplication.
Yeah. So the intuition that I'm getting is this: the first method is definitely applicable to the counterexample, whereas this one, it is kind of applicable for kind of any inputs, right? So
correct. So the first one is the counterexample guided measure.
This is
and this one is the reverse measure in some sense. When we are abstracting, we are looking at the weight difference being the least. Here we are looking at the weight difference being the most.
Okay.
Okay.
So Devjit, is that clear? So what?
Sort of. I mean,
what is it that is not clear to you? Was the first one clear?
So just give me some time. Okay. Yeah.
Okay.
Actually, yeah. But like, I think I get the basic idea.
Okay.
I think you should go ahead. Yeah.
Yeah, you should go ahead. I'll understand this.
Okay.
Correct. Yeah. So yeah, so while abstracting, we are looking at a heuristic which was telling us to abstract something where the weight difference, we were trying to minimize the weight difference. Here we are trying to maximize the weight difference. So basically, you when you are abstracting, you first merge the ones which have the least weight difference, then you merge another one, maybe the weight difference increases over a period of time. And then when you're refining, you first refine the one which has the maximum weight difference. But while refining, you also have the counterexample with you, and therefore it will be good to be guided by the counterexample. And therefore they also suggest this other measure. And in order to get one final answer and not get two different answers from these two measures, so they suggest that you can look at the product. Okay. So this product suggests that V1 has to be. Okay. So now if you notice, see, when we are trying to merge these two, remember that, we were looking at, which ones to merge, and we decided that, V1 and V3 should be merged first. Okay. And now when we are trying to split, we are seeing that V1 should be removed first, which will leave you with a merge of V2 and V3 and V1 alone. Okay. So so what I'm trying to say here is that, you can get different abstractions here. So it's not that, because the refinement tells you to remove V1, the abstraction would not tell you to merge V2 and V3 if you ask at this point. Okay. So at this point, the abstraction could tell you to merge V1 and V3. And then when you ask which one to throw away, then it can tell you, okay, throw away V1. Okay. So it can be, it can be a little, it need not be symmetric in that sense. Okay. So that's one thing that I wanted to add. Okay, so once you have the abstraction and the refinement, there is a CGAR algorithm, and the algorithm is very simple. It says that, you generate an abstraction, then you try to verify your property. If your property turns out to be so if you try to verify your property, if your property is not, if it gets verified, which means that, so you're basically checking if a counterexample can be found. Unsat means that a counterexample cannot be found. No counterexample could be found.
Yeah. So here it's important to emphasize, if the property is P, I guess Devjit, okay. So why is unsat being checked here? I just wanted to make sure that all of you understand that. So why is unsat being checked? Can you tell?
So like, we have to check that if the property, okay, just a sec. So
there is one thing you see. So the P is the property. You want to check that it holds good for all value. So
Yes. So we
so
are
the
doing
way
an
that your
over up.
validity, checking validity using SAT, how do you do it? You take the negation.
Oh, yeah, yeah.
That's all. So if P is the property that you're verifying, then you, of course, it is being verified on the over approximation. You take the negation and you check the unset. Okay, because that's how you check validity. SAT only checks satisfiability or things. So validity is checked by taking the negation and then checking if it is unset. Okay, so if it is unset, then you return. So that's what. So the implicit thing here is that you're taking the negation and check the unset. Yeah, that's the answer that we should have given. Yeah. Okay. Go ahead.
So we were doing over under approximation, right, of n.
No, we are doing an over approximation. Right?
Okay. Okay.
Yeah.
Oh, yes. Oh, yeah. Okay.
Huh?
Yeah. Okay. Yeah.
Okay. Yeah. So instead of asking that, does the property hold always, we want to ask the other question: is there a case such that the property does not hold? Okay. So instead of asking this question, does the property hold always, we ask this question: is there a case such that the property does not hold?
But that is true. But the thing is, that it's for that you take the negation and check the unset. No.
Yeah.
Yeah.
Yeah. So this becomes a satisfiability question. Is there a case is a satisfiability question?
Yeah, but the important thing is it is the negation. You do the SAT checking on the negation.
Correct. Because you cannot get this. Is there a case on as long as you don't do a property does not hold.
That's what does not hold. Yeah.
Okay. So this is what. Okay. So when you get an unsat, then you're done. If you get a sat, which means that the satisfying assignment, which is a counterexample, like like the 1-0 counterexample that we had seen in the last page, in the last slide. So you get a counterexample, then you can check whether this is a real counterexample or not. To check whether it's a real counterexample or not, you simulate it on the original network, not on the abstract network. Right? If it's a real counterexample, then you're done. If it's not a real counterexample, you refine. So when you refine, you try to get a different network, and then this new network is once again an abstraction. It's only a better abstraction than before, but then it is still an abstraction, so you can start all over again. You can check whether the property holds. If it does not hold, then you will get a counterexample. And this CIGAR algorithm is very common. See, this algorithm does not talk about what is the abstraction procedure, what is the refinement procedure. Okay, so this is a general counterexample guided abstraction routine. As long as you have any way of computing an abstraction and any way of doing a refinement, this is you can plug it in this algorithm. Okay, so in that sense, it's a general thing. Okay.
Yeah, but there's one question that I want to ask, just to keep the folks on the toes. So I guess whose turn is it now? Back to Ameya. So yes, what Madhukar said, you could use any refinement, you come up with a new refinement. But what is the guarantee this terminates? Any of three of you can answer. So not just, I don't want to put Ameya alone on the spot. Why does this? I mean, for the refinement that Madhukar explained in the last few slides, this definitely terminates. Or in general, if you come up with your own method, why should this terminate?
Yeah, either you fix the counterexample or you have found the counterexample.
No, but so the refinement that Madhukar showed, it was pointed out that it may not fix the counterexample right away. Okay.
Yeah, but after a
few,
few,
it terminates. Why? There is some very important property that refinement has to satisfy. Okay. Madhukar already mentioned that. Okay.
I mean, if you do a lot of refinements, then you will end up with the original network.
That I understand. So use refine. So the key word that Madhukar used is this n bar prime is quote unquote better than n bar. Okay, the refinement has to ensure that when you do the refinement, what you get is more accurate. That's what it means to be better. It is more precise than n hat. Okay,
Right.
because each step is in each refinement step is replacing your original abstraction with a more precise one. In this case, by splitting one node, okay,
Right.
then eventually it keeps on even in one step if it doesn't improve. So, eventually you will end up eliminating that counter example, okay?
Or like you might end up with the original network if you refine it.
That is also there. Yes.
And then you will terminate.
Worst case, you will end up with the original.
Yes.
Correct. The hope is that you don't you convert.
Yeah, you get something better, but not the original thing.
Correct. Yeah. So that's the thing. So my question was about the guarantee that I think you answered. Yeah. So you can come up with your own refinement method and plug it in there, as long as it ensures that refinement is really increasing the precision, okay, in some sense over the previous abstraction. Yeah. Sorry, Madhukar.
Yeah, no, yeah, that's important. Yeah, so let's look. Yeah, so I think this covers the abstraction refinement part. Let's look at one of the things, a couple of things that I've not I've told you about, but I've not really covered. So one of the things that I told you earlier is that with the restriction of having only one neuron in the output layer, it may seem too much, but it's not very limiting in the sense that there are still interesting properties that you can verify. So for instance, let's look at this particular network and this property that you want to verify here, that y2 is bigger than y1 or y2 is bigger than y3. So y2 is either bigger than y1 or it is bigger than y3. So if you want to verify this kind of a property, it doesn't fall into the standard y less than equal to c. Sorry, y greater than c thing that we want to. Y greater than c. So this is the property. This is the template of the property, and the q, which is the negation of the property, comes as y less than equal to c. Q is the post condition. Okay. So this is something that we had seen, that the restriction was that the property can only be of this form, y greater than c. And here we see that this property is certainly not of this form, and there are more than one neurons in the output layer. So they claim that, look, this restriction is not very limiting, because you can certainly do these kind of properties, but you can do a bit more. You can do some more kinds of properties. For instance, if you have a property of this kind, then what you can do is you can extend this network into such a network here by adding more neurons after the output layer. So for instance, in this example, they have added one layer here and one here, such that now this T1 is y2 minus y1, as you can see, and T2 is y3 minus y2. Okay, and so one of them becomes so this becomes y2 minus y1. So this becomes y2 minus y1 is greater than 0. That they can check that y2 minus y1 greater than 0, or y3 minus y2 minus y3 is greater than 0, right? Now, instead of checking that they are individually greater than 0, they can check that this z, which is the maximum of 0 comma y2 minus y1 and 0 comma y2 minus, so T1 and T2, which are max of 0 comma y2 minus y1 and max of 0 comma y2 minus y3, they sum this and they say that now this should be greater than 0. If this is greater than 0, then individually both of them are greater than 0, right? Because this is, none of them can be so if this is 0, then Oh yeah, then at least, yeah, sorry. So if Z1 is greater than 0, then at least T1 is bigger than 0 or T2 is bigger than 0, which means that at least Y2 minus Y1 is bigger than 0 or Y2 minus Y3 is bigger than 0, which essentially tells you that either Y2 is bigger than Y1 or Y2 is bigger than Y3. Does this make sense? Am I connected?
Yes. I mean, like you are just rewriting the.
I'm just rewriting and putting it into the, I'm just saying that, the restrictions that we had on the network and the property, the restrictions on the network and the property are not as limiting as they seem. There are some, there are networks which do not fall in the restriction, and there are properties which do not fall in the restriction, which can be transformed into, a network and a property which falls in the restriction.
Yeah, is there an example like which you can't transform?
I think there are many things which you can't transform. I'm sure it will be easy to find an example. I've not thought about it, but
I think remember that he's using only greater than here.
Correct. So if you have a property saying,
which
Y1 is
greater than, less than, or equal to in arbitrary Boolean propositional combination, you're in trouble. Okay.
Correct. So if you have Y1 is equal to 2 times Y2.
Yeah.
Plus Y3.
See, but I think the main idea, the takeaway here is that what is being done is that the property is being encoded as a DNN. Okay.
Right.
As a DNN. Now, if you're able to encode your property, maybe there is a larger class that you can be smart. If you could encode it as this is a Boolean combination that you're trying to do, and then if you can encode it as a DNN precisely, then you can do it. So
I mean, I was thinking like, since you could approximate a lot, you could approximate a lot of these properties with a DNN, but not precisely.
Yeah. So, but since you're checking actual formulas, you have to be able to do it precisely.
Right.
So that's what. But there was a side observation that I wanted to make here. Okay. Now, obviously, this you could, of course, the original method worked only for a single this thing. I mean, single y greater than c, the kind that Madhukar just showed. What you're having here is an arbitrary formula. Now, the question that I'm raising is, obviously, you use the same abstraction refinement method, but use the general power of a full SMT solver, because SMT solver, after you do it, it can check any arbitrary formula. But I don't know if somehow, but then whether if you had no, I'll take it back. I mean, I don't think you can do that. Anyway, so no, I don't want to confuse, further. So I haven't thought that through. I was going to the idea that since you do have, if you feed it to an SMT solver, this kind of a thing, it is able to handle anything but nothing. Anyway, so the limited point that I wanted to make, I've already made. Okay, so correct. I think the point is that if you can encode precisely as a DNN, you could do it. Okay. And we have already seen some things which is may not be able to do accurately. That is a combination of less than or equal to greater than and so on. With disjunction, okay? As long as it is only conjunction, you still will be able to do, okay? Even with less than or equal to and greater than, because it's still linear. So you can encode it precisely using linear transforms.
Right. So
once you start having disjunctions, then you need to put some restrictions in order to be able to precisely do it. Okay. Is my take. Yeah.
Right.
Correct. So in general, the problem with having multiple neurons in the output layer is that, remember that, our technique tries to, it takes one neuron. I mean, it assumes that there's only one neuron in the output layer, and then it tries to get a bigger value here. And according to this, it understands whether there is an internal neuron which is increasing or decreasing or positive or negative. correct? And it does all the classification with respect to one at a time. Now, even if there are, so since the output neuron is the last layer, and suppose, you have a property of this kind, so you can have properties of this kind, right? Y greater than C. So if you want to verify, Y1 greater than C1 and Y2 greater than C2, then you can make two copies of the network, one where you keep Y1 and forget all the other output neurons, and one where you keep Y2 and forget the other two output neurons, and you can individually check this, and you can check this also individually,
Yeah,
right?
but
Yeah.
that is true. But you can also encode it easily using having a DNN equivalent to that. No? So it is easy to see how you could encode it here. It's a little bit harder to see how you encode disjunctions. Huh? So there.
Correct.
So why do you? Yeah. So you don't need to. You can use the same technique of what he has shown here to encode this property as well. Huh? This conjunction, no? Yeah.
Correct.
Like, we'll have to think about it.
I think conjunction is easier, is what I claim, okay? Because you will have to make sure that the output is 1 when both are true, okay? When both are true, okay? So when this is true, you will, you will get a 1. When this is true, you get a 1. So by adjusting weights, like 1 and 0, etc., and taking differences, you will do it.
Oh yeah, you can just write like if you have 1 and 0, I think, and add them. Just
So
like,
adding them, your output should be 1. Okay.
right.
So that the output is 1. So when you add them, if both of them are 0, then your output will be 0. Okay. That is the case that you should not. That should be false. So you add the outputs of checking these two things, and then which can be done using difference. Okay.
Mm-hmm.
So that's why my claim is that conjunction is much easier. You can always do it, and disjunction is what requires a little bit doing this max and so on.
Correct.
Yeah.
So you just need, so you have conjunction, disjunction, and you now need just a knot.
Yeah. But we are still restricting ourselves to greater than.
Right.
So then you can, if you extend that to any arbitrary linear, I mean, less than or equal to, greater than or equal to, with disjunctions and conjunction, then it's not clear. You can always encode it. Okay.
Yes. No, but like a not negation would still be nice.
Yeah. Once you use negation, it is similar to combining greater than and less than or equal to. Huh? Because negation of greater than is less than or equal.
Right.
Oh, okay. So maybe I'm sorry.
Yeah. No. Yeah. I think, yeah. So this is pretty much all that I wanted to say. I just wanted to take you through, just give you a glimpse of, what this could do. So
maybe you could say, since there will be something about, go ahead with your thing. So one thing, additional thing that I want you to point out, or even if you don't want to cover, is about the implementation. Okay. No, not full deal about implementation. If they want to use this, where is it implemented if there is a tool that they
correct. Yeah. So I'll talk about this, but yeah. So before that, I'll just show them the paper. And okay, so this is the paper. It's uploaded on Moodle already. And there's one more thing that they said, which was about an indicator guided abstraction. So remember that we had, I told you that you could go and you could merge every pair that is there available for merging, right? So you could take anything which agrees on the increment decrement classification, and also agrees on the positive negative classification, and take any two such things and go ahead and merge them, right? And you can there's nothing stopping you. You can go all the way till you have nothing more left to merge. Right, but an alternative they suggest is that you can also do what is called an indicator guided abstraction. So for indicator guided abstraction, they said that let's start with a bunch of points, okay, which satisfy this should not be the property P. This should be the negated post condition. Okay. So while all the points satisfy the negated, so you go on abstracting till all the points satisfy the negated post condition. So this is some indicator that you can use. You can start with a bunch of a bunch of points, and then every time you do an abstraction, you can check if all your points still satisfy the post condition or not. The first moment where one of your points starts to not satisfy the post condition, you could stop. You could say that, look, this is some indicator that I have abstracted too much. Okay, so this is, of course, this is the concept of an indicator guided abstraction is to use some indicator, and here they have used a bunch of points as an indicator, but it need not be this indicator. You can come up with your own indicators. And so in that sense, this algorithm of abstraction refinement is you can plug and play different. You can plug different heuristics for abstraction, you can plug different heuristics for refinement, you can plug different heuristics for how much to refine, or how much to abstract, which layer to abstract, which layer to refine, and all that. But this whole framework of a counterexample guided abstraction refinement will still give you a sound answer. So that's one thing that I wanted to cover before coming to. Okay, so the important thing in the implementation is that, first of all, it's available. You can they have given a link to the tool in the paper. You can find a link to the tool, and they have done experiments. So I'll give you the key points in the experiment first, and then maybe, if there is interest, we can look deeper. So they took 45 DNNs, deep neural networks, from this benchmark called ACAS, or this airborne collision avoidance system. And the input is a set of sensor readings. We have looked at some picture earlier that told us about this. Okay, and there are 5 output neurons, turning advisories left, right, clear of conflict, etc. Okay, so what is the size of these networks? This is about this is 300 hidden neurons plus 5 input neurons, which are the sensor readings, and 5 output neurons, which are the turning advisories. So this is 310 neurons for every network. Okay, so there are 6 hidden layers of 50 neurons each, and so that's 300 plus 5 neurons for the input, 5 for the output. So this is 1200 neurons. So this is 310 neurons. And if you assume that everything becomes 4 times when you do the positive, negative, and the increment decrement split, so this can lead to potentially 1200, of the order of 1200 neurons after the transformation. Okay, so some of the findings are as follows. So first of all, they said that the abstraction to saturation, which means that you abstracted everything that you could, it outperforms indicator guided abstraction. So they had used some points as indicators, and in this case, for their examples, the abstraction to saturation worked better than indicator guided abstraction. Okay, so I think this is for a bunch of properties. The original network has 310. Remember that it could potentially increase to 1200, but then they merged it, and on an average there were 269 nodes that were there in the network when they proved a bunch of properties. So even though this doesn't seem too much, this is a lot, because the complexity is exponential in the number of neurons. So even if you save by 10-15% of neurons, this is a considerable amount of saving. Okay, and there are cases, in fact, that the neurons, the set of the number of neurons at which
if I can stop you here. So see, from 310 they go to 1200. Okay, after that, merging everything to saturation will reduce to 4 per layer. Correct.
Correct. So about some 20.
Yeah. So if it is 6, so then they keep refining. So then they got back to 269.
Correct.
So the reason I was thinking was how many refinement steps that was needed. Okay, I guess it is from going from 65, because they had 6 layers, six times 24,
24 plus 10.
24, and then at each refinement step, you would add 1, correct? If they were using their original head. So they needed quite a few, isn't it? Okay.
Correct, correct.
60 to 269. So yeah, okay.
Yeah. So there are some, in another set of experiment, they saw that, there are cases when you increase the size of the network eventually from 310. But, after you have done the positive, you separated the positive negative thing, and, after you have done the split, what you have is a simpler network. So even in some cases, when the number of neurons increased, this still turned out to be faster. Okay. And they claim that, this is because simpler queries can sometimes be better than smaller networks. So even if you have a small network, if your queries are not very simple, if your SMT queries are not very simple, then it may take up a lot of time. In some cases, it's even better to, it turns out to be better to increase the size a little bit, as long as you are able to get simpler SMT queries. Okay. And yeah, so of course, this is just one set of experiments. Then they did another set of experiments on adversarial robustness. And for this, I'll show you from the paper that this was still better. Okay, yeah, here.
So what do you mean adversarial robustness? Like, could you elaborate on that a bit?
Okay. Yeah, sorry, I couldn't hear you.
I was saying, like, what do you exactly mean by adversarial robustness?
So by adversarial robustness, so I think this is the property where robustness is.
Yeah, in simple terms. So let me make it simple. So adversarial robustness is if you perturb your input by a certain amount, okay, will the result, the expected result, still hold at the output?
Like, it doesn't diverge. So
it doesn't
diverge too much.
Yeah, it does. No, it does not. Yeah, it has to give correct results. Okay, so it may diverge, but it is within the tolerance to not change the result. Okay.
You add some noise to the input, and it shouldn't.
Exactly right. That's it. Yeah.
Right.
That's how. Yes. There are some variations of these. Yes.
Correct.
Perturb your input, your output should still be, produce the same result.
Okay.
Correct. Yeah. So that's in general about a network is supposed to be robust. If for some sensor data, let's say if you're giving some advisory, then for another piece of data which is close to that, you should continue to give the same advisory. And it's called adversarial robustness because we are trying to check, is there any deviation which is small but for which you get a different advisory.
Like, this could be useful for one of those image, one pixel attacks where they add just a pixel to the image and it changes.
True. Yeah.
Yeah, in your project, you can even consider these kinds of properties if it makes sense. Yeah. See, because robustness properties, he qualifies it as adversarial. I define it as robustness in general. Maybe there are other kinds of robustness. I don't know, Diganta, if there are other kinds. Anyway, so just a side comment. Okay, so you could, when we discuss that, you can consider other kinds of properties for your project. Okay, I hope you are thinking about your project. So the standard thing, but most verification with DNN they do is such adversarial robustness properties. Okay.
But for text, like, how would it make, like, if you just change one character on the text?
Yes, maybe it doesn't make sense. Okay. So,
it does make sense. Like, for example, if you made a mistake, like, for example, instead of that, THAT, you write THET. So the output should still think of it as that, and it shouldn't diverge too much. If you change one character in the input, it shouldn't change the output.
or I was thinking, this may be too clever. If you replaced words with synonyms.
Oh, nice. But
Yeah, now that I don't know, Diganta, if you try, in your training thing, I mean, ideally, I would like, okay, that may be too smart thing. I don't know. Anyway, we're digressing from Madhukar's thing. Okay? So,
Yeah, if I'm nearly done anyway. So I was saying that, for robustness properties, they said they showed that, I mean, they saw that the query could be solved in an average of 104 nodes as opposed to 310 nodes in the original network.
yeah, so I think you should talk about implementation. So so they can read this thing up on their own if they are interested. The reason that since we're also running out of time, okay.
Correct. So so this has been implemented in a tool called Marabou. Marabou is available.
The question is, I don't want you to give details of implementation. That will take too much time. So how they can use it, or whether is it worthwhile to even consider using it based on the stability of the tool. For example, in trying to verify their RNN system. Now I know it doesn't apply for RNN because after all, but they're reducing RNN to FFNN. So from that point of view, so that's what if we could, you can describe the implementation. I'm not asking you to describe implementation in detail, but the question of whether they can use it is worthwhile using, even considering.
So I think this can be used. The details are available, and I think Diganta has used this tool already. So if you get stuck, you can ask Diganta how to use it. So Diganta has used this tool already, and I think this is So in a bunch of papers, I think Reluplex certainly reports certain experiments, which is also implemented in the Marabou framework. And then on top of Reluplex, this abstraction refinement is implemented in the Marabou framework. And of course, as Sir pointed out, for the RNN thing also, when we had to check whether a proposed candidate was actually an inductive invariant or not, we had changed that problem into a feed-forward neural network verification problem. And for that also, they had used this Marabou framework. So in general, I think this Marabou framework has been used quite a bit. There are some restrictions, certainly, that you cannot have, you can only have ReLU nodes. You cannot even have MaxPool nodes, which are typically used in classification networks. But there's some way to encode MaxPool nodes into ReLU nodes.
Let's be more specific. Okay. So Diganta, what is your experience on having used it? Number one. Number two, does it even make sense for them to use it for their project? So so that's all that I wanted. Yeah.
Yes, I have used Marabou only as far as the Reluplex algorithm goes. So
only Reluplex. You have not used the abstraction refinement thing.
Yeah. And the Reluplex is fairly stable. It makes a lot of sense to use the Reluplex part of it.
That they will certainly use, okay, because that they'll have to use, because that's the only one that they have. I mean, unless they want to use SMT, which will not scale at all, okay? So Reluplex that they'll have to use. So none of us has had, I don't know, Madhukar, you have had experience. So maybe, you guys could, do you have independent experience, Madhukar, of having used it or no?
No, I have not used the Marabou framework.
Yeah, the abstraction refinement thing.
Not used this part.
Okay, so that's the thing. I mean, let's see. So, so in your work, you will have to use Reluplex, certainly. But if you are guys, depending upon how successful you are, if scale or the size becomes an issue, even for Reluplex, then you could consider. But I think there are other problems that you'll have to first overcome in your thing, okay? Of encoding your properties and so on. So, yeah, so very soon we'll have to have a discussion on that. Okay, so anyway, so that's the thing. So,
so yes, the only one comment that I have is that, so it allows support only for ReLU, which is fine. Mostly, you will only deal with networks that have ReLUs. But whenever you have a classification network, there's some MaxPool layer, and you can encode MaxPool using ReLU. So that's one way of, again, using the Marabou framework, even if you have max pool nodes.
Yeah, that itself, that restriction itself rules out the use of it, because for this system that Diganta has proposed, there's lots of other kinds of functions, correct, Diganta? Like tan H and so on and so forth. Huh? Hello, Diganta?
Yeah, hello.
Yeah, did you understand my
Yeah, I'm saying that.
brought up? Yeah?
Yeah. Those issues will be there over here.
Yeah, so it is out of question. Okay, so but even for ReluPlex, there is some kind of encoding that you'll have to do, I think, because ReluPlex is also only Relu. Okay.
Yeah.
Yeah. Anyway, so that's an issue. So you already have certain nonlinear issues there. Huh? Okay. We'll have to worry about. Yeah.
Yep.
Yeah. So that plus property encoding, that will make your hand pretty full. So in any case, we can't use this abstraction define, but it's nice to know, okay, that there is something, that is available, okay, for, yeah.
So is this too late for Diganta to start?
I think so. Diganta, I think it may be best.
Should I talk about another? I mean, very
Yeah,
brief
but
idea
it's
about
still
another
very
paper.
late. Okay, see, so it's 4:50. So if indeed we want to do it, we might as well do it in leisurely, huh? Instead of rushing it in 5 minutes. Can you, I'll leave it to them, okay? So, you have to make a choice, because it's 4:47. So you have.
Yeah, I think it's better to stop now because I have a class at 5 also. So
Okay.
I think we can
Yeah. So it's okay then.
continue next
Start.
class.
No. I think we can revisit it, okay, as another abstraction mechanism. So,
yeah. So it's not very deep. So in the sense
no,
that
it's not very deep, but it may still require about half an hour or so. No, if you want.
Yeah. Yeah, so maybe I'll let Diganta complete the discussion on permutation invariance, and I can revisit it towards the end of the course.
Yeah. So there's still, let's plan on the remaining thing. I'll make up a schedule, okay, by scheduling also their presentations.
True.
Okay, and then we'll see how where we are. Okay? Yeah. Is that okay? Is that agreeable for all of you?
Yeah.
Okay, we'll do that. So I think next time Diganta will speak, and you have to be ready to discuss the project. Okay. At some point, because I don't want to put it off too much, because then you'll be you guys will have nothing in hand. Okay? Because there are some issues that some of which maybe we can get things. So you have to come yell and scream, okay, to see what your problem that you're facing, and that you cannot yell and scream unless you get your hands dirty, okay? Which I'm concerned that whether you have even got your hands mildly dirty at this time, okay? So I will let you speak. Not now, okay, later on, yeah, in the next class, yeah.
Okay, sir.
Yeah, okay.